Okay.
Okay, so last time I went quite fast. I'm sorry for that. So I'm going to just recap what we have so far. We're working towards the proof of the Pila-Wilkie theorem. The first thing we've done is the parameterization result. So that said, if I have a natural number R and X R, first thing is I have a fixed O-minimal structure expanding the real field. And when I say definable, I mean definable in there. And then I have a subset of the open unit cube, which is definable. Then this set has a cellular R parameterization. And the cellular, the fact that this is cellular means that it automatically implies a uniform version. So corollary, suppose I have X is now a family parameterized by I to the m. Then there's an n such that for each parameter, the fiber over that parameter has a parameter, an R parameterization. So R in n has an R parameterization by at most n maps. Such that for each a in I to the m, if the fiber is not empty, then there is R parameterization of the fiber with at most n maps. So the number of maps you need is independent of the parameter. So this follows, so you could either prove this, in the proof of parameterization, we needed this when n was 1. And you, like there I used saturation. You could do it using saturation, sorry. But the cellular nature of the maps means it's automatic as well. So what you do is you take a cellular parameterization of all of X, and then you just you look at the maps which, so fix the value of A and look at the maps whose image intersects the fiber, and you take A back and you plug it into the parameters. And because the map is cellular, that makes sense. You see the cellular maps are compatible with the coordinate system, so you can move A back on its own. So I'll leave the details as an exercise. But the point is you use the cellular structure of the parameterization. So you apply the theorem to the whole set X. Okay, what else do we have? So that was like the O-minimal bit that we did, and then we had the Diophantine bit. So what did that say? Well, we had K, N, E, and D positive integers. With n bigger than e, d at least e plus 1 times n. And then this tells us that there is an R positive integer. R and reals C and epsilon with the following property. And the property is if you have an R times differentiable map on the unit cube in K space going to N space, and you look at its image, you suppose that the map is R times differentiable with all its derivatives bounded by 1, and you look at the image, then the algebraic points of degree at most E and height at most H on that lie in some H to the epsilon many algebraic hypersurfaces. So this gives us the hypersurfaces that the points we want to count lie on. So let me write out that property. Or suppose phi map size to K to I to the N is CR with phi alpha x less than 1 for all alpha in N to the K of order at most R and all X. And let's let X be its image. Then for H at least 1, the set X, E, H. So this is the points on X. All of those coordinates have degree at most E over Q and height at most H. This set is contained in at most C, H to the epsilon algebraic hypersurfaces of degree less than or equal to D. And as we take D bigger and bigger, so as D tends to infinity, this epsilon tends to 0. Okay, and those are the two main ingredients. Let me state what we want to prove, and then I'll start proving it. So this is the Pila-Wilkie theorem. So suppose I have a definable family. I have an E at least 1. Actually, in this form, the Pila-Wilkie theorem is due to Pila. So E at least 1, epsilon greater than 0. Then there is a C such that for every parameter and all H, the number of points on the fiber, on the transcendental part of the fiber, degree at most E and height at most H is most C H to the epsilon. So what do I mean it's due to Pila? So the Pila-Wilkie theorem is this with E equals 1. And then Pila proved this version where you allow points of bounded degree. But as I said last time, we'll follow the proof that Near Bardwaj and Al van der Dries gave recently. So let's start. So I know I started this last time, I'm repeating. So it's by induction on N. Now the first thing I can reduce to is that all the fibers, so this R to the N, I can replace with I to the N. So you do that using the maps, X maps to plus or minus X to the plus or minus 1. we can assume, so these preserve rational points of height at most h, or algebraic points degree at most e and height at most h. So we can assume that xa is contained in, so these get us into the closed box for each a, and then if they meet the faces, we can just use induction. Then using induction, we can assume that xa is contained in I to the n for each a. And we can also assume that the parameter space R to the n is the interval or the box. We can also assume that x is actually contained in I to the n times I to the n. Okay, now, so what do we do to start with? So we've got our epsilon. Now, I use this, the Diophantine proposition. So given a k less than n, I can take d so large that the epsilon provided by this is less than epsilon over 2 for my epsilon in the theorem. And I can do that for each of the k's less than n, sorry. So then I get a bunch of r's and c's. And I take the r to be the maximum of all of those. So for each k less than n, take d large enough that the epsilon of k in dE provided by the Diophantine proposition is less than epsilon over 2. And then, so for each k, I then get an r and a c, and I let r and c be the max of the resulting r and c's constants. And then I apply the parameterization result here with that r. So then I get an n such that each fiber has an r parameterization with at most n maps. So by our parameterization result, there is an n, so it depends on x, e, and epsilon, such that for each a, the fiber xa has an r parameterization with at most n maps. So if I look at the image of one of those maps, then the Diophantine proposition tells me that the points of degree at most e and height at most h lie on c times h to the epsilon over 2 algebraic hypersurfaces. So then I put all those together and we get that the points of degree at most e and height at most h on the fiber lie on the most n times c times h to the epsilon over 2 algebraic hypersurfaces. So for each A and H, the fiber, the points of degree at most E and height at most H on the fiber contained in the union of at most n times c times h to the epsilon, but epsilon was less than epsilon over 2. That sounds wrong when I say it like that. Hypersurfaces of degree at most d. So then given this, so it suffices to show that there is a C. Yeah, C is going to differ each time. Hopefully that's not a problem. There's a C such that if P is a polynomial, has degree at most D, then the number of let me write this out. So this is the fiber intersected with a zero set of P. I take the transcendental part, and then I look at the points of degree at most E, height at most H. I want to show this is less than or equal to C times H to the epsilon over 2. Since if I can show this, then I have at most, then when I look at the whole thing, so the transcendental part of this is going to be contained in, sorry, I just want to say, right, each of the points here is going to lie in some hypersurface like this, like this rather. And then for each of those I have a bound, and I need at most this many hypersurfaces. So I get less than or equal to the number of hypersurfaces times the bound here. And that's CH to the epsilon. So this is what we need to prove. Okay, so to do it, let's let F be the set of all of these P's. So be the set of all non-zero polynomials in n variables of degree at most d, considered as a definable set. So viewed as a definable so a definable set in the real field. So it's just R to the n, where n is the number of monomials. So identify the polynomials with their coefficients. and then you remove the 0 one. And then I can let curly v in f times r to the n be the family of all hypersurfaces of degree at most d. So be the, again, it's r bar definable family whose fiber over P is just the hypersurface that's cut out by P, the 0 set of P. So such that Vp is equal to V of P, the 0 set of P, for each P in F. So now I can apply cell decomposition in the real field to get there are semi-algebraic sets C1 up to CK such that their fibers over P, the union of their fibers over P is VP, and then for each J, the fibers over P of CJ are a cell, and like a fixed type of cell. So I'll write out what I mean, such that for each P in F, VP is the union of the fibers, and such that for each J from 1 up to K, there is an IJ sequence of zeros and ones of length n, not equal to all ones, such that for each P, the fiber CJP is either an IJ cell or empty. So remember that this is telling me in each variable as you go up, your cell is either a graph or a space between two graphs. And it's 0 if it's a graph, 1 if it's a space between two graphs. You can't, sorry, this should be not equals. You can't be this one because then you'd have an interior and we have a hypersurface. So we don't have interior. Okay, so attached to each of these, there's a projection which gives a homeomorphism from a cell of that type onto its image. For J and Ij as above, let pi, I'm sorry, this notation I could have done better. So this goes from, so this is the projection corresponding to these. It goes from Rn to Rnj, where Nj is the sum of the components of Ij, So ij1 jn, and that's less than n because we've excluded the 1, 1, 1, 1. Be the coordinate projection mapping C J P homeomorphically onto its image. Now, this projection, what does it do? It just emits some coordinates. So if you're a point of degree at most e and height at most h, then your image under this projection is going to be a point of degree at most e and height at most h. So as it just emits some coordinates, it sends points of degree most e, height most h, 2 points of degree at most e, height at most h. Now we need a lemma that I proved last time. I'll state again. So this was so the following: let S in R to the n be semi-algebraic, and F an ejective semi-algebraic function and if I have a subset of S such that F restricted, so a subset X of S such that F restricted to X is a homeomorphism onto its image, then F of the transcendental part of X is the transcendental part of the image. So if X in S is such that F restricted to X, sending X to Y, the image of X, is a homeomorphism, then F of X trans is Y trans. So we proved this last time. And now we're going to apply it with these cells are going to be our semi-algebraic sets, and these projections are going to be our homeomorphisms. Okay, so that's on the side. So let Y J, so this is going to be a definable family of subsets of R to the nj with its parameters will be in I to the m and f. So it's the definable family with fiber the definable family such that for a point AP in I to the m times f, the fiber is the image of XA intersected VP under the projection corresponding to J. So it's pi I J of XA intersect, sorry, CP, not VP. So I take this, I project it down, and that's my fiber here. And then by this lemma, the transcendental part of this is the projection of the transcendental part of this. And because these projections send points of degree at most e, height at most h to points of degree at height at most h, the number of points of degree at most e and heights at most h on the, there's a bracket missing, on this thing here is going to be at most the number of points of degree at most e, height at most h on this. So we also have the thing we're interested in this is contained in the union of these. For each AP. Now, by the induction hypothesis, I can do the counting on these. So there exists a C. Well, so I get one for each J, but then I can take the maximum of them over the J's. So there is a C greater than 0 such that for each J and each AP in I to the n times F and each H, the number of points in Y, AP trans EH is less than or equal to CH to the epsilon over 2. But then this is at least the number of points on this. So I apply this to each of these, and I get a bound on this. So hence, for each AP and H at least one, number of points on XA intersect BP trans EH is less than or equal to, so I've got K things, so K each bounded like this. But K is independent of H, so that's less than or equal to CH to the epsilon over 2. And that's what we wanted. So that proves the Pila-Wilkie theorem, following the proof of Bargrach and Vanderbies. So the thing that really makes it all work is semi-algebraic cell decomposition combined with this lemma. And it really is quite a bit simpler than the proof that Pila-Wilkie gave originally. And I think Nia presented it much better in this talk. So there's a video of that on the Field's website you can watch. Okay, so that's the Pila-Wilkie theorem. So the next thing I was going to talk about was applications of the Pila-Wilkie theorem. So this is now a bit different. So there have been a lot of applications of it recently, or in the last 10 years or so. So I'm going to focus on one or two for some references. So Scanlon has at least 3 survey papers on his webpage that you can look at. They kind of increase in order of difficulty. I can't remember their names, but they're easy to find on his webpage. There's a paper by Habeger and a paper by Martin Orr. These are both in proceedings. From a summer school in Manchester. So I will put proper references for these. I'm going to upload a file of references once I've finished the lectures. But these are some things to look at for this section, and I'll give more references later on. Okay, so let's see. So the applications I'm going to talk about concern elliptic curves. So suppose K is a subfield of the complex numbers, and an elliptic curve over K is a smooth projective algebraic curve defined over K of genus 1 equipped with a distinguished point that lies in K, or whose coordinates lie in K. So that's the abstract definition, but then there's a more concrete one. So any such E then has a Weierstrass equation given like this. So y squared equals 4x cubed minus g2x minus g3, where g2 and g3 are elements of my field K, and they satisfy g2 cubed minus 27g3 squared is not 0, so that's going to make the curve smooth. Well, this is an affine equation, so that is E is isomorphic to the curve in P2 cut out by the projectivization of this. Given by zy squared equals 4x cubed minus g2x z squared minus g3 z cubed. And the only point missing is the point corresponding to B0, which is the point at infinity on this projective curve with P0 corresponding to the point 0, 1, 0, which is the only point missing. From the Afon part. So you can think of, for our purposes, you can think of elliptic curves being given like this. And the, well, a very important fact about elliptic curves is that if I look at the points with coordinates in my given field, K, then they form a group, an abelian group. So the K rational points EK form an abelian group, and this P0 is the zero of that group with identity element P0, and the group operations are given by rational functions with coefficients in K. With group operations given by rational functions with coefficients in K. So the group structure is given by the chord and tangent process. So I'm not going to try and draw the pictures for it, but if you haven't seen it before, you just Google it, you'll get nice pictures. So what we're going to do is prove a special case of the following. So this is due to Raynaud. So it says that so I'm stating it in a more general case that will prove it. So that A be an abelian variety. So if you don't know what that is, we take what we will prove, which is A is E squared with E as above. Defined over C. And then let A tor be the torsion points. So the points that have finite order on this abelian group. Then what the theorem tells us is that the, well, we need to let V be an irreducible algebraic subvariety of A. Then, when I look at the points on V and I intersect them with this torsion, this is the risky dense in V. If and only if V is related to the group structure of A. So if and only if V is an irreducible component of an algebraic subgroup. Of A. So what it's saying is that the only way you can get to risky dense torsion is the way that you get to risky dense torsion. So if you're a component of an algebraic subgroup, then general theory of abelian varieties tells you that the torsion is risky dense. So the content is in the other direction. And in the other direction, what it's saying is, if the torsion is risky dense, then there's a kind of group theoretic reason for this.
Hey,
Okay.
Gareth, can't you have a coset of a subgroup?
Yes. My algebraic subgroup might not be connected.
Sorry. Oh, sorry. Right.
So a
right.
coset is an irreducible component.
Sorry. Yes. Yes. Thank you.
Okay, so right, so I should say that this statement, there are much more general statements now. Much stronger and or more general statements are known. And this theorem's from the 80s and has, like, it's been generalized and improved in lots of ways, but it's still quite an influential result. So one way you can generalize it is that your abelian variety could be a general commutative algebraic group. You can replace torsion with kind of points of small height. But I'm going to focus on this in the case where A is E squared. So the point is that this is one of the easiest examples of how to apply Pila-Wilkie and Gareth problems. So we will prove this in the case A is E squared. Using proofs, well, Raynaud proved this, and then there are other proofs, including one by Hrushevsky, and then there's a later proof by Peter and Zani. That's what we'll give. So using, and it's called, the method is called the Peter-Zani method. And it has various ingredients. And in this, we see most of those ingredients. There's kind of one that we don't really see, which appears in more complicated problems. We won't prove it in that case. We'll prove it in the case A is E squared with E defined over a number field. Okay. So like I said, the general theory of abelian varieties shows that if you're an irreducible component of the subgroup, then the torsion is risky dense. So the difficult direction is the other one. It's to show that if V is not contained, or is not a component of a subgroup, then V of C intersect A tor is not risky dense. And that's what we'll do. Okay, so we write N like this for multiplication by n. So the multiplication by n map on E or A. So A from now on is E squared. So note that if I have a point P in En, which is the n torsion, so it's the points of finite order for dividing n. So this 0 is the P0 from above. If I have P in there, then P is algebraic. Okay. And if I have Galois morphism, then sigma of P is also in here. So the Galois group acts on the n torsion. And this is very important for this proof. And the other proofs as well. But what's also important in this proof is the analytic picture. So fix a bias stress equation for E as above, then there is a unique lattice in C. So that's a discrete subgroup of C of rank 2. Such that the following hold. If we let P of Z be given by this series, so I take the sum over all non-zero lattice elements of this, and add 1 over z squared, and then this defines a meromorphic function on C. It's periodic with respect to the lattice, so that means if I take a lattice point omega, P of z plus omega is P of z. For omega in omega. This function has poles of order 2 at the lattice points, and those are the only poles. And it satisfies a differential equation, which is the same as the bias stress equation. So, oh, well, it's not the same. You put P prime in for Y and P in for X. So what this means is that if I send z to p of z, p prime of z, then I get a point on my affine curve. So this induces a map, which I'll call pi. So I send z to this point, so an affine point, if z is not a period, a lattice point, and I send it to the identity. Otherwise, and this map is a surjective group homomorphism, surjective analytic group homomorphism. Surjective complex analytic so apologies if you can hear hammering happening somewhere here. I don't know where. Okay. So the numbers G2 and G3 are related to the lattice as well, but we don't need that. I mean, they're given by summing a certain series of lattice points. But, okay, so what does this map do for us? So omega's a lattice in C, so I can fix a basis of that lattice, a z basis, which will be two elements of the lattice which are linearly independent over the reals, and then they such that they generate the whole lattice. So fix a basis, fix a z basis, omega 1, omega 2 for my lattice. Then I can think of C. I can put a different coordinate system on C, so I identify it with R squared using omega 1 and omega 2. So I get the following map. So it maps R squared to E. And I send B1, B2 to pi of B1 omega 1 plus B2 omega 2. So this is a surjective real analytic group homomorphism. So it's just putting different real coordinates on C. And once its kernel, so its kernel is the points such that this lies in the lattice. So because these are generators of the lattice, that's exactly z squared. And then the pre-image of the torsion points on E is exactly q squared. And we get that the torsion is isomorphic to q mod z squared, and the end torsion is isomorphic to z mod nz squared. Okay, so what's the idea of the Peterseniere proof is that using something like this, you can identify torsion points with rational points, and the order of torsion is related to the height of that rational point. Now, if you've got your V, so suppose V is a curve containing an E squared, and it's not a component of a subgroup, then we want to show it has finitely many torsion points. So we're going to take a restriction of this map to get definability and look at the pre-image of our curve under that restriction to get an analytic set in R squared, real analytic set in R squared, where rational points on that real analytic set will correspond to torsion points on the curve. And then we can apply Pila-Wilkie to that analytic set. So that's going to tell us that there aren't very many points in the Pila-Wilkie sense of order n. On the other hand, if you have a point of order n, you get a bunch more by the Galois action. And then there's number theoretic results which tell you that the degree is relatively large in terms of n. So it's going to be bigger than some power of n, some positive power of n. And that's going to contradict the Pila-Wilkie theorem, or at least tell us that the algebraic part of our set must be non-empty. So if the algebraic part was empty, it would contradict the Pila-Wilkie theorem, at least once n is large. So then we have to see what happens if the algebraic part is not empty. And that's where we use what's called a functional transcendence result. And that implies that you end up having to be the kind of thing we said we're not. So you have to be a component of the subgroup. So yeah, the other ingredients are what's called Galois bounds. So that's the thing that tells us that a torsion point of order n has relatively large degree in terms of n, and functional transcendence. So that's going to tell us how having a non-empty algebraic part means that there's some kind of group structure. So I'm going to now give the proof, modulo these two things, and then either today or next time, I'll show how you can prove these two things, or I'll sketch proofs of these two things, or well, sketch ideas of proofs of these two things, both using counting. So the proof of this, you only need Pila-Wilkie. The proof I'll give of these, so originally the things that I'll say here were proved in other ways, but I'll sketch a proof where you use an improved form of the Pila-Wilkie theorem. Okay, so proof of special case of Lindemann. So we suppose A is E squared, E an elliptic curve, defined over a number field, K in C, V contained in E, an irreducible algebraic curve, not contained in an algebraic subgroup. Sorry, E squared, A. B contained in A, an irreducible algebraic curve, not contained. In a proper algebraic subgroup, we want to show that there's only finitely many torsion points on B. So to do this, we'll show that if P is a torsion point of order n, then n is bounded. And then, because there's only finitely many points of bounded order, there can only be finitely many torsion points on B. Okay, so I got my irreducible algebraic curve. I could assume V is defined over K as well. Well, I'm only proving it the case where it's defined over the algebraic closure of K, because otherwise I think you automatically get finiteness. And then we can just make K bigger to assume that it's also defined over, V is defined over K. Right, so put F to be this thing. So I take the half open interval and square it and remove 0. And then square that. And then I'll let B be the following. So it maps F to E of C to A of C. And it sends B1, B2, B3, B4 to this in each coordinates. This in each coordinate. So pi B1 omega 1 plus B2 omega 2 pi of B3 omega 1 plus B4 omega 2, where omega 1 and omega 2 are fixed as above. So then B is definable in Rn. Now, I haven't really talked about Rn at all. You can just take my word for that. But if you've seen the definition of Rn, then this is quite simple. And I'm going to assume that Rn is O-minimal. I mean, Rn is O-minimal. I'm not going to prove that. But I think probably that's been proved in Andre's course. I had to stop going, so I don't know. Or I think he's probably proved much more general things, which in particular imply the O-minimality of Rn. Okay, so B is defined with Rn, and what's its image? Its image is almost all of A. So it's a projection onto its image, which is A minus minus the things that I've taken out. So minus those two copies of E. Now, we're assuming that V's not contained in an algebraic subgroup. So that means its intersection with this must be finite. V of C intersect this. Is finite. So it's enough to prove that there's finitely many torsion points on V lying in the image of B. So if I show that there are finitely many torsion points, V squared intersect the image of B. So what's my analytic set? My analytic set is going to be, I take, so I've got V on this side and I take its pre-image under B. Let X be inverse of V of C. So B is defined in Rn. V is an algebraic curve, so it's certainly defined in Rn. So this is a definable set in Rn. Now, if I take a torsion point of order n on V, then its pre-image under B is a rational point of height at most n. So if P in V of C intersect AN, well, if it lies in the image of B, then its pre-image Q is a rational point on X. And in fact, Q lies in 1 over n times z to the 4 intersect X. So its height is almost n. So we can apply the Pila-Wilkie theorem to X. So we get for all epsilon, there is a C such that for all H at least 1, the number of points on X trans Q H is less or equal to C times H to the epsilon. So let's call this C epsilon. Okay, so what's the other ingredient I mentioned, the Galois bound? So this is in this case, it's due to massa. So this is a weak version. So A is as above, and so is K. Then there exists C prime and a delta positive, such that if I take a torsion point on A of exact order n, then the degree of the field I get by adding the coordinates of B to K over K is at least C prime n to the delta. Okay, now if sigma is a Galois automorphism. Let's fix, sorry. Suppose I've got a point. Of order n. If I have a Galois automorphism, well, then sigma b has order n as well. And lies in V, because V is defined by equations with coefficients in K, sorry. So this Galois automorphism sends a point like this to another point like this. Moreover, if the point I start with is not in the exceptional set, the E times 0 union 0 times E, then neither is the other point. So if P is in the image of B, then sigma P is in the image of B as well. Because the image of B is also defined by, or rather the exceptional set is defined by equations over K. So the pre-images of these points, these sigma of P, all give rational points on X of height at most n. Pre-images of the sigma P under B all have height less than or equal to n, and there's lots of them. So by Masser's theorem, what do we get? We get that the number of points on X of height at most n is at least C prime n to the delta. Okay. So this isn't quite a contradiction, because here I've got X and here I've got X trans. So what do we get? Well, so if I apply Pila-Wilkie here with epsilon, say delta over 2, from 1 with epsilon equals delta over 2, and 2, we get, well, either X alg is not empty, or C prime, this is less than or equal to C n to the delta over 2, and this implies n is bounded. So this is what we wanted. So in the latter case, we're done. So we have to see what happens in this case. So suppose X alg is not empty. So what is X alg? X alg is the union of all connected infinite semi-algebraic subsets of X. So if X alg is not empty, then there's some semi-algebraic curve contained in X. Now, x was got by putting a different real coordinates on c squared. But when we change the real coordinates, we still preserve being a semi-algebraic curve. So the fact that there's a semi-algebraic curve contained in x means that there's a semi-algebraic curve contained in pi inverse of v. Well, okay, so if I write, so before I had pi going from c to e, if I now have it going from c squared to a, for that map, so it's just pi in each coordinate, x was essentially pi inverse of v intersected with, or restricted, except that I changed coordinates. But that real change of coordinates preserves being semi-algebraic. So then there is a semi-algebraic curve so there's a semi-algebraic analytic, real analytic, gamma, non-constant. So it sends, so it's a curve in, sorry, that's a V. So V is our algebraic curve in A. And what we get from the algebraic part of X being empty is a semi-algebraic curve in the pre-image of V. So from this, it follows that there's actually an algebraic, the complex algebraic curve in the pre-image of V. So this complex algebraic curve, y, contained in pi inverse of V, well, an irreducible one. So to see that, so I've got gamma, so it goes to c squared, which I can identify the answer for. So write gamma, gamma 1, gamma 2, gamma 3, gamma 4, and put z1 of t to be gamma 1 of t plus I gamma 2 of t, z2 of t, gamma 3 of t plus I gamma 4 of t. Then these are algebraic over these. So C Z1, Z2 is contained in the algebraic closure of R gamma. Now this, well, R gamma has transcendence degree 1, so this has transcendence degree 1, so this has transcendence degree 1. R gamma has transcendence degree 1, and it follows that this does. Well, so that means that there's an irreducible curve. Complex algebraic curve y with these being in y. And so these are also in in pi inverse of v, so then the intersection of y with pi inverse of v is infinite. So by analytic continuation, y is contained in pi inverse of v. So y is infinite. Y intersect the intersection, the pre-image value is infinite. So y is contained in the pre-image. Okay, so we've gone from having a real algebraic curve to a complex algebraic curve. Then we can use the following theorem, which is kind of overkill here, but let's state it anyway. So this is what's now known as Lindemann Theorem. So I have a. So I'm going to state it in a general context. I have an abelian variety over C of dimension G, which you can take to be E squared, like we have been, pi its exponential map, which is the pi we've had already. V is a complex subvariety of A. So that's our curve above. And Y is a maximal irreducible complex algebraic subvariety of the pre-image. So maximal here means if you have another irreducible complex algebraic subvariety of pi inverse of v which contains y, then it is y. Now the y we have here is maximal, just because this is one-dimensional and this is one-dimensional. So we're in the setting of this theorem. And what does the theorem then tell us? Then pi of y is a translate of an abelian subvariety of A. Okay, so this is what's called a Max-Lindemann theorem for being varieties. So next time I'll say a little bit about the proof of this. I think it must be overkill in the case we're in, but I didn't quite see why. But it certainly does what we want. So let's finish the proof. So what do we get? We've got all of these things. So applying this in with all of this stuff here, we get that pi of y is a translate of an abelian subvariety of A. Now pi of y, so y is contained in pi inverse of v, so pi of y is contained in v. and they're both one-dimensional. V is one-dimensional irreducible. This is algebraic, one-dimensional. So they're equal. So since V is one-dimensional irreducible, they're equal, and V is a translate. Of an abelian subvariety of A. So it might be a translate by a non-torsion point, and then it doesn't have any torsion points on it, so we're done. Otherwise, it's a translate by a torsion point. And then it's a component of a subgroup, which contradicts our assumption at the beginning. So it's a component of an algebraic subgroup contradicting our assumption. So we get finites of torsion points on our V. So that's the proof of that special case of Manet-Mumford using the Peterseniere strategy. So maybe I won't start what I was going to start now. I'll just talk a little bit. So this Peterseniere strategy, it works in lots of settings. So what's it doing? You've got some kind of algebraic objects of a special kind. So here we had an abelian variety, or the square of an elliptic curve. And you've got some special points on that. So here there were torsion points. And you've got this uniformizing map pi, under which, perhaps changing coordinates, special points correspond to rational points. So you have the same thing if you look at, say, C star to the n. So here, special points would be torsion points. So they'd be points, all of whose coordinates are roots of unity. And then you have a map. Well, pi, I guess. So pi sends like Z1 up to Zn to x of 2 pi I Z1. And here, when you have a point here that's a torsion point, it's going to have coordinates that are all roots of unity. It's going to correspond to a rational point here. And you can do the same, like it's just another instance of the general Manet-Mumford result. You take a subvariety here, and its intersection with the torsion is going to be governed by the subgroups that live on it. And the same proof will work. So roots of unity have large degree in terms of their order. So you'll get lots of conjugates to help you beat the Pila-Wilkie theorem. So that was already known as well. Those are odd results. But then there's other results. So if you can consider, so we talked about elliptic curves. So most elliptic curves have endomorphism ring Z, but some have a larger endomorphism ring, and they're said to have complex multiplication. So elliptic curves are determined up to isomorphism by elliptic curves over C are determined up to isomorphism over C by a number called their J invariant. So you can think of elliptic curves as being parameterized by C, and then you can take pairs of elliptic curves, and you can look at a curve in there, and you can ask, are there infinitely many points on V corresponding to pairs of elliptic curves with complex multiplication? Question. And the answer is that there could be, but the V's for which there obviously are special, and the André-Oort conjecture in this case, so a special case of André-Oort, it determines all such V. So it says if V is not of one of the following special forms, then there's only finitely many points on it, which correspond to pairs of elliptic curves with complex multiplication. So that was proved by André, but Pila gave a different proof using the Peterseniere method. So here, the map pi that we had before is replaced with the J function, and now it sends instead of rational points in the pre-image, you get points of degree 2, so imaginary quadratic points, but you can still count them using Pila-Wilkie because you have this version with the bounded degree in instead. And yeah, I mean, then this is a special case of something called a Shimura variety, and this whole picture works in Shimura varieties. And I guess September or October last year, the proof of André-Oort for Shimura varieties was completed using the Peterseniere method, except that, I mean, all of the other ingredients are much more complicated. but yeah, they're now known. Okay, so next time I will sketch how counting can help with the Ax-Lindemann-Weierstrass thing and how it can help with the Galois bounds. Okay, thanks.
Thank you, Gareth. I stopped the recording.